let's begin. If any of you are going on that bridge visit today to see the I-64 bridge in Nitro, please meet in the lobby no later than 2 p.m. They're going to hand out the hard hats and high-vis vests and then drive over to the site. I think the people who are signed up have already got an email with the address, but even if you're not signed up, there's still spots available, so just feel free to show up, and they'll be glad to have you go along. And if you haven't yet RSVP'd for the homecoming barbecue, please do that today if you're planning to go. I think it's a great opportunity to network and get to know some of the alumni. Our program's been around long enough now that some of our alumni are getting into pretty senior positions throughout the employers in the region, so I think it's good to get to know people, even if you have a firm job lined up for after you graduate. You never know if you want to switch, or just having good relationships with people in your Marshall network, I think, is a good use of your time. And then one other thing I wanted to bring to your attention is the Employer Spotlight Series. I know some people have already gone to those, but they're from 11 to 1 on Wednesday the 26th for special medals, and Wednesday the 9th of November for the Army Corps. And if you'd like to attend that, then you can go to that. It'll be considered as an excused absence for our class. And I've started recording the lectures, and so you'll be able to catch up that way. If you're interested, then you should email Tanner Drown to RSVP for the Employer Spotlight Series.
What do civils do at special medals?
I don't know what they do, but I know that they have hired some of our civil engineering graduates. Did you say something?
They told me they just sat in an office because they have a degree and they fill space.
Yeah, right. Special medals, I think, I'd like to think that they run a...
That's honestly what one of them told me.
Yeah.
He says they just hire them because they need somebody to sit in the office that has the degree.
All right.
Perfect, Jeff.
So,
is that what you were thinking, Jeff?
I mean, it sounds like a pretty good job.
So today we're going to talk about sanitary sewer design, and we've covered some of these topics in the 331 class before. And we're going to actually just begin with some detailed nomenclature. Sewer collection networks are dendritic in nature, meaning that pipes connect to other pipes, and it fans outward with an increasing number of pipes the further away you get from the treatment plant where all the water's flowing to. And it's hierarchical, meaning that the names that they give to different pipes kind of convey the relative size of the pipes. And the next slide after this is going to illustrate these different pipes and how they kind of fit together. But at the top of the list would be the smallest diameter pipe, which is collecting wastewater from either a home or a building and taking it to the main sewer that would run down the usually center line of the street. So those are laterals. Mains are what collect water from laterals and take it to the intercepting sewers that could be a trunk line or an interceptor. Just the intercepting sewers are things that gather together multiple mains. Now, distinguishing between a main, which would be gravity flow, and a force main is that a force main is a pressurized pipe where water is flowed usually into some sort of a collection vault, and then there's a pump that pumps the water through a pressurized pipe in order to lift the hydraulic grade line. In locations where there's really flat ground, you're not able to have a continuous, uninterrupted downward slope for the pipe because the pipe would be getting continuously deeper and deeper and further from the ground surface. So in flat areas, they have to occasionally have the water lifted back up closer to the surface and then continue on down in the gravity flow. Or there may be other locations where it's just hilly and force mains have to be used to move wastewater from a low-lying area to another part of the network. And our book talks about how it's pretty common to see force mains along shorelines. You know, construction or neighborhoods that are close to lakefront or along the sea oftentimes will have to use pressurized pipes to get the water towards the treatment plant. A trunk is any pipe that has accepted several different mains together and is conveying it towards the treatment facility. And there isn't much to distinguish a trunk line from an interceptor, other than in larger cities where you have lots of trunk lines coming together, then they usually designate an interceptor as something that's accepted 2 or more trunk lines. So it's just the nested hierarchy is that when you have 2 mains coming together, the next one would be called a trunk. 2 trunks coming together, the next one would be called an interceptor. So here's an illustration that shows that the lateral is the pipe that conveys wastewater from a home to a main. And of course, if there are basements in an area, then the main needs to be buried lower than the lowest occupied floor in a building. And so that's one consideration in design of how deep does the sewer have to be, is whether people typically have basements. And around here, I don't know, there are some basements I know in developments in Huntington, but most of the houses I've been in don't have much developed beneath the ground surface. I think that's probably just, it varies from place to place depending on the water table depth. The connection to the main is usually not, from the side view, you maybe would be forgiven for thinking that it comes in at a 90-degree angle, but it's usually angled in a direction so that the laterals entering, so that the flow is in the same direction as the sewage flow, and having that helps to eliminate clogs and makes it easier for maintenance, because oftentimes mains are cleaned on a periodic basis where they've got trucks that will flush the sewer out to try and remove any kind of debris that's settled at the bottom of the pipe, or if they're doing inspections. Just for a variety of reasons, it's advantageous to have the lateral entering the main at an angle. And then when there are really deep sewer mains, then you may have to have a riser which takes the sewage down from a lateral which is relatively flat and sloped down to the main. Now, this top view showing kind of a schematic of a development that has many different laterals coming from homes and buildings joining together in the mains, and then when several mains come together, then they're calling these the trunk sewers. Manhole distances is governed by, for one thing, the slope of the pipe, where you have relatively shallow slopes and there's more of a risk of sludge and solids settling to the bottom of the pipe, then maybe you need to have a more frequent spacing of manholes. But in locations with less flow variability and steeper slopes, then you maybe could get away with having the spacing increased a little bit between manholes. And the purpose of the manhole is just to provide a location that the sewer can be inspected and accessed for cleaning. So we call it a reach, the distance between 2 manholes. And here you can see the interceptor is designated as the largest downstream pipe that's accepting several different trunks together. This diagram is showing that there is a force main, and we don't know from the top view what would be the reason for the force main. It could be that it's draining sewage from a low-lying part of town, but this overview just kind of illustrates the fact that it would be common practice not to have the pipe diameters decreasing in the network. If your laterals are 8-inch, then the mains would have to be larger than that, 12-inch, 15-inch. Then the interceptors that collect from multiple different mains together, those would be increasingly large in size, even if from a hydraulic standpoint, if you had one reach that was relatively steep, and the pipe diameter from a hydraulic perspective could be relatively small because of that slope, it still would be uncommon and ill-advised to have a small diameter pipe just because of the risk of clogging. So pipe diameters always increase in the direction of flow. We talked about in class on Wednesday that it about in the early 80s became more common to have rubber gaskets where pipes come together to reduce the effect of inflow and infiltration, but then also to prevent the leakage of sewage into the groundwater. So kind of a dual advantage there. This cross-sectional view of a pipe is important because it helps us to see that the invert, when we use that word, it means the bottom of the pipe, the crown is the top of the pipe. But this punch is the underside of the pipe that is really important to take into consideration when you're burying a pipe. I think contractors could sometimes get in a hurry when burying pipe, and if you think about a trench and pipe in a trench, if they were just scooping the soil on top of the pipe, then it wouldn't necessarily, the soil wouldn't get down underneath the hunch unless they specifically tried to pack it under there. And so if there isn't fill under the hunch, then that provides a lot of stress for the pipe and it has more of a risk of cracking. But if they do support the hunches, then that can increase the strength and limit infiltration and inflow concerns over the years, because little pipes turn into larger, little cracks turn into big cracks over time. So kind of the takeaway constructability concern that our book addresses is, number one, the importance of having a really flat bed, because any kind of high points or low points in a bed that has a very rigid pipe that's made out of concrete is going to cause that concrete pipe to crack lengthwise. But then also packing soil underneath the hunches is a way to prevent the pipe from coming under too much stress when it's loaded with soil from above, or when vehicle traffic is driving over it, for that matter. It's typical to have manholes that are large enough for people to get down into in order to remove debris or to be able to visually inspect, but cameras are getting much smaller, and fiber optic cameras and remote controlled inspection systems are kind of making it less important than it used to be for people to be able to get down into the sewer, and especially because it's just so risky to have people going down into the sewer because the fumes that can accumulate there, hydrogen sulfide in particular, are really toxic and dangerous, and because of the risk, it's always a pretty big operation setting people down into the sewer where someone has to remain at the surface and kind of keep an eye on the person who's working to make sure that they haven't become overcome by fumes, and to rescue them if they do get into trouble. And so I think it's still common practice to have person-sized manholes when you've got sewers that are being installed, but less important than it used to be because of remote inspection technology. This is a sketch, and there's some related discussion in the book, of an inverted siphon. And an inverted siphon is a kind of novel approach to moving water in a pressurized pipe section, but you're using gravity to do it. So there's no pump required, but in an inverted siphon, water is entering some sort of an inlet chamber, gravity flow, meaning that this pipe has some wastewater, but then it's not flowing full. Above the wastewater is just air. But as the water enters this inlet chamber, this inverted section is a pipe that's going to be flowing completely full. And so they may have a drop, like an induction section, where the pipe is losing some elevation to try and cause all of the sewage to fill the pipe. But the key to the inverted siphon is that the outlet chamber and the downstream end of the pipe is a little bit of a lower elevation. And you've probably seen siphons before where, think if you submerged a garden hose in a swimming pool and you got all of the air bubbles out of the garden hose, and then you kinked one end of the garden hose and you left the other end in the pool. So the kinked end of the garden hose you could take down a hill and then unkink it, and then water would start to flow through the garden hose. That would be a siphon. So it doesn't matter where the middle of that garden hose is, as long as the outlet end is lower than the inlet end, then water will flow through that garden hose. And so an inverted siphon like this is similar in principle, except for it's carrying wastewater, and that inverted section could allow us to go under a stream, under any kind of low part of a neighborhood. It's just a way to carry wastewater under pressure without having to use a pump. So when opportunity allows, then inverted siphons can save some money since the electrical costs are such a big part of what contributes to the expense of treating and moving wastewater. Any questions so far? All right, well, let's talk about pipe sizing. I know that many of you already are familiar with Manning's equation, and for those of you who aren't, this is a formula that we can use to relate for a pipe how much water, like the flow capacity of the pipe as a function of the cross-sectional area of the pipe, the slope of the pipe, a roughness coefficient, which is N, and then the wetted perimeter. And so if a pipe is flowing full, then it's relatively easy for us to calculate the cross-sectional area and the perimeter of the pipe. And especially in wastewater, it's almost exclusively just going to be a circular shape for a pipe. So pi d squared divided by 4 is the cross-sectional area of a circle, and pi d is the wetted perimeter of a circle where this pipe is flowing full. And so what Manning's equation allows us to do is predict how much water could be carried by a certain pipe if there's a given slope. And here the notes are saying that S is the slope of the energy grade line, but the energy grade line, the hydraulic grade line, and the pipe are all the same slope if you have open channel flow and if it's steady. So open channel flow means that the pipe isn't necessarily under pressure, and so we can use the slope of the pipe in sewer sizing. And you may wonder how it could be both open channel and a pipe that's flowing full. One interesting thing about sewer hydraulics is that if you've got the water almost all the way to the top, but not all the way to the top, the flow capacity of a pipe that's mostly full is actually larger than a pipe that's all the way full. So if we have the same diameter pipe, and so this one's full, this one's mostly full, so the Q of this exceeds the flow rate of that. So I'll see this Q mostly full exceeds the flow capacity of the full pipe. Anybody have a notion of why that might be, that a pipe that's, let's say, 90% full is going to have a higher flow capacity than one that's filled all the way to the top?
Friction.
Friction. Yeah, the additional friction. If the water's all the way to the top, then there's the contact with that concrete, usually, surface at the top that's inducing a little bit of extra drag that isn't there for the mostly full pipes. So we can use Manning's equation for pipes that are flowing all the way full and they are under pressure. But even when we use Manning's equation for a pipe that's full, we still don't distinguish typically between the slope of the energy grade line and the pipe slope. So just, you can usually assume that for sewer hydraulics, we're using the pipe slope as S naught. And if you have a forced main, which is flowing under pressure, then typically it would be better for us to move over to the Hazen-Williams equation, which is a different formula from this. But forced mains are relatively rare. Most of the pipes in a sewer network are going to be open channel flow and designable using Manning's equation. But most of the time, these pipes aren't flowing full. Remember that we would have the pipe sizing so that it's full on the peak hour of the peak day at the end of the many, many years of development. You know, when the neighborhood is completely built out, we want the pipe to have enough capacity to handle the peak day, the peak hour of that fully built out time, maybe 25 or even 50 years in the future. So most of the time, like 99.99% of the time, the pipe is going to be carrying much less than its full capacity. And so to know how deep the water is, the situation is a little bit more complex. Because pipes rarely flow full. We could use Manning's equation if it was all the way full, but for partly full, what we have to do is look at the angle that the water line makes with the center of the pipe. So here, if we measure the angle in radians, then we have a series of equations that allow us to know what is the water depth, h, relative to the diameter of the pipe. And when we know the angle, we can calculate the cross-sectional area, the wetted perimeter, and then substituting that into Manning's equation, we've got a very different looking version of Manning's equation that's based on that angle. So this is kind of, when we use programs like StormCAD or SewerCAD, which are software packages that that we can use to analyze the hydraulic performance of a pipe network. They're using equations like this in order to predict what the flow is. So the other complicating factor is that here in this Manning's equation, that there's a different n value that we have to use compared to if the n value was a pipe that's flowing full. So this n value, for assuming full hydraulic capacity, is different from the n value when the pipe isn't flowing full. So there's a table that's both in the EPI reference manual, our textbook has a copy, the hydraulics book has a different copy, and they all look pretty much the same. It's a nomograph that illustrates how, for different depths, how Manning's n value changes. Or I guess what we could say, this is the effect of that thing I drew on the board. The fact that when you've got relatively less wetted perimeter, the effect of the roughness is reduced. So this is how we account for the effect of the n value compared to when it's full. So you'll notice here, this is saying the n value relative to the n value of when it's full. And so we'd read that across the top, and then across the vertical axis here is the ratio of the water depth to the pipe diameter. And so there's a couple of different ways to use this nomograph. You could calculate the full capacity of a pipe and then use this curve to find out the partially full capacity relative to the full capacity. Or you could find the updated n value and apply that updated n value in this equation. So what I wanted us to have some time to take a look at is how to analyze a pipe when we have flow conditions that aren't full. And by the way, what I showed you here, this value of Manning's equation is for SI units. If we're working in traditional units, meaning feet for the length rather than meters, then we have to add 1.49 to the front of that. So in this example we're going to look at, this is traditional units, and so the Manning's equation we're going to use as 1.49 as a units conversion coefficient built into Manning's equation. Okay, so we're going to just step through this together, both using the nomograph method, and then I'm going to show you what the angle method would be like if we wanted to kind of calculate it directly without having to find the full flow rate first. Okay, so this is a 24-inch diameter concrete pipe, which is flowing on a 0.5% slope, and the depth of flow is 9 inches. Now, we want to know what is the flow rate when the water is going at 9 inches depth. How much water is in that pipe to cause it to flow at a depth of 9 inches out of 24. So, first of all, just using the nomograph method, we have to find out the full pipe capacity. So, I guess what I'll do with the recording is I'm going to do some of these calculations on the whiteboard, but then I'll bring it up on the screen in a bit to make sure it's brought into the recording. Okay, so the diameter here is 2 feet. the depth Y is 9 inches, which is 0.75 feet. Our N full is 0.013, and the slope is 0.005. Okay, so the first thing, to find the full capacity, we're going to substitute that into Manning's equation with the 1.49 units conversion. So 1.49 times the area. So let's over here off to the side calculate the area is pi d squared divided by 4. So the area of this pipe is 3.1415 square feet. And then the wetted perimeter, pi d, is 2 feet times pi, so that's 6.283 feet. Okay, so into Manning's equation, we're going to have the area of the pipe, which is 3.1415, and that's feet squared, to the 5/3 power, and then the slope 0.005 to the 1/2 power, and then divided by n value 0.013, and then the wetted perimeter 6.283 feet, and that wetted perimeter should be the power of 2/3. So while I go get a different marker, I'd like you to calculate what is the capacity of the pipe if it's flowing full. So hopefully what you found is that the full capacity would be 16.04 cubic feet per second. Now, what we need to do is go to the nomograph and try and find out where we intercept this curve. So our ratio of Y to D is 9 inches out of 24 inches. So that was 16.04 cubic feet per second. Now Y to D is 9 inches out of 24 inches, which is 0.375. So on this curve, we need to find, here's 0.2, 0.3, so we want 0.375, so 3/4 of the way between 0.3 and 0.4. So over here, then we go to the point of intersection, and then up. So it looks like it's most of the way towards 1.3, because here's the line for 1.3. Here's 1.2. So what I estimated that the, oh I'm sorry, we're doing the Q, not the N value. Wrong curve. All right, so we're going over here from 0.375 to the point, to the intercepting the curve of Q to Q full. So that is here and then down. Okay, so Q to Q full is, I said 0.24. So if we had this printed out, you had a ruler and all that, 0.375, intersect, and down 0.24. Let's just go with it. With Q to Q full is 0.24. And so therefore, the flow rate when it is 9 inches of depth is going to be the flow rate of 16.04 cubic feet per second, multiplied by this ratio of 0.24, and that is 3.85 CFS, cubic feet per second. Okay, so I had the full flow of 16.04 CFS. Given this Y to D, intersected the Q to Q full curve, which was this one, 3.75 down to 0.24, All right, so any questions about how we would use the nomograph to find the flow rate based on the full flow? All right. Now the other approach is to try and calculate the angle, the area using this formula, the wetted perimeter using this formula, and then finding the ratio of n to n full, and then substituting all of that into Manning's equation. So let's start by finding the angle. So the angle, I'm going to erase what's on the whiteboard now just to make some extra space. Okay, so theta is 2 cosine to the -1 power 1 minus 2 to the y to d. So the y is 9 inches and the d is 24 inches. So that's the same as some calculators have it listed as ACOS. At least my calculator does, the inverse cosine. So on the inside there is this 1 minus 2 times 9 divided by 24. That is 2 times ACOS of 0.25. So those Casio calculators, is it cosine to the -1? All right, so what do you get for cosine of inverse cosine of 0.25? Oh, by the way, you need to be in radians, is the other thing. So if you're in degrees, switch into radians. And I was in degrees. So, okay, I think I'm in radians now. 0.25. Inverse cosine. Josie, did you get it? I'll just wait till you do. Anybody got it? Alex?
3.64.
That's not what I got.
2.64 is what I got.
For 0.25?
Well,
Did you
times
multiply?
2, you gotta multiply by 2.
Oh, okay, yeah, so I just meant on the inside. Okay, so yeah. So, yes, if the angle altogether, okay, good, yeah, sorry about that. 2.64 radians is the angle. Okay, so is it more than half full or less than half full? Well, if it was pi radians, that would be half full. So it's less than half full, and that kind of confirms what we already knew. You know, like it's 9 inches out of 24. So that gives us a little bit more confidence that this angle, you know, is within expectations. If it was more than 3.14, then we maybe would know we had a numerical error. Okay. So that is the angle. And now that we have the angle, we can calculate the area and the wetted perimeter. So the area is theta minus the sine of theta times d squared divided by 8. Boy, these are bizarre formulas, aren't they? So 2.636 minus the sine of 2.636 times the diameter of the pipe, so 2 feet squared divided by 8. So it's pretty odd, I think, that you'd have an angle minus the sine of the angle in the same equation. But that's what we're doing, and remember, it needs to stay in the radians mode for calculating the sine of the angle. So when we do that, what we should get is that the area of the flow is 1.076 feet. That's not the area of the pipe. That is the area of where the water is in the pipe. So if this is a 24-inch diameter pipe, then this area is 1.076 square feet. Alright? Now the wetted perimeter that we're talking about is likewise, it's not the entire perimeter of the circle. We just want to know where is the water in contact with the pipe material. So this is the wetted perimeter. So we can calculate the wetted perimeter with this formula, R times theta, or D divided by 2 times theta. So P is D divided by 2 times theta. And so that is 2 feet divided by 2 times 2.636 radians. Okay, so 2.636 feet is that distance there, 2.636 feet. Now, we also need to find an updated N value, because since it's not flowing all the way full, there's just a discontinuity between the way that Manning's equation is calibrated and how much of the pipe is contacting the flow. So we need to come up with an adjusted N value for our Y to D. So we already, in our previous step, found that Y to D was 0.375. And this time, we're going to go up to the upper axis to find the intersection point. So the Y to D is 0.375. So here over to this curve, the N to N full, find the point of intersection, and up 1.27. So N to N full is 1.27. So then that means that the N value is 1.27 what was described. So the problem statement said that when the pipe is flowing full, it's 0.013. This is going to be more than that because less of the flow area is far away from the pipe wall. You know, like if the pipe was more full, then more of this flow area would be away from where the resistance is applied. So that's why the N value here is higher, 0.01651, is because there's relatively more resistance since less of the flow area is away from the boundary where the shear stress is applied. Okay. So let me show you how then we could substitute all this into Manning's equation. We know the area, we know the wetted perimeter, we have a new updated N value. So this is showing how we calculated the angle. We used the angle to determine the area, the wetted perimeter, updated N value, and substitute that into Manning's equation. And we get that the flow rate is 3.78 CFS. Compared to the way we did it before, that's less than 2% different. And that's to be expected since we're just kind of eyeballing values off of this nomograph. We were eyeballing the ratio of N to N full. And in the earlier problem, we were eyeballing the ratio of Q to Q full. So I feel pretty good about the fact that these two methods agree as closely as they do, given the curve that we used. So partly full pipe hydraulics is a complicating factor that most design software handles in the background, and you may not even be aware of it. But I think it's good that you kind of know what the considerations are, and especially because you know, there could be questions related to this at the exam.
Or
we gonna make giant spreadsheets again?
Giant spreadsheets? I don't know. Probably not. I think that the homework problem that you'll have related to pipe hydraulics for this class will probably be pretty mild. All right, that's all the time we have for today. No homework on your plate at the moment, but I'll try and put one together and we'll talk on Monday. If you are planning to go to the bridge tour, even if you haven't signed up, you're welcome. Just meet in the lobby at 2. Unfortunately, I don't get to go. I'm headed to a meeting, so you'll have more fun afternoon than I will.